Hello everyone. In this video we will talk about using the definite integral to compute area between curves. So let's start out with an application of computing area between curves and see why we might be interested in studying such a thing. Okay? So first I want you to recall a fact from Calc 1 when we first talked about the integral. So if we have a definite integral of the derivative of a function, then we can view this as the net change. It's kind of a geometric or real world interpretation of this. The net change of the function f from a to b, right? And often this might be from like time a to time b. And that's maybe the example you want to have in mind, right? So the classic example would be that f is distance traveled, or your position function. F prime is the velocity in that case, right? And so if we take the integral from a to b of f prime, here I'll say f prime of t dt because we'd be considering time, right? This would be the net change in distance or the displacement, right? From time a to time b. So how does this correspond to area between curves at all? Well, let's consider the following situation. So I'm going to start with a graph, and we'll have this on the y-axis be the velocity, and we'll have time down here. And then we'll look at two different things. So first we're going to look at what our car is capable of before we soup it up. So before, we'll just say before improvements. And let's just say that its velocity, if we, are trying to accelerate it, say, to go from 0 to 100 or something, right? So maybe it looks something like this. And then let's say we have the souped up version. So we've got the before and after. And let's say it looks something like this, right? Souped up version can go a little bit faster. So a natural question might be, if I am starting at time 0 here and then I am driving for, I don't know, let's just say 10 seconds, okay? Then how do I know how much farther can I travel in these 10 seconds than before, after improvements, right? Well, one way to look at it would be, I'll start with all of this, right? Area under the curve is going to be total distance, right? Because we would be integrating the velocity and finding distance traveled. And then I could do the distance under the red one and see how far I traveled, and then just subtract the green away, right? And so that would be a very natural way. And if you subtract the green away, well, I mean, that takes away all the stuff under, and suddenly, what is this net distance that we have improved? It's exactly the area between the curves, okay? And so how would you actually calculate that? Well, if this is like F1 and this is F2 for, kind of the first and then the second, then this would literally just be the integral from 0 to 10 of F2 dt, so F2 of t dt, minus the integral from 0 to 10 of F1 of t dt. And this actually happens to be true in general. All right, so this is just the more formal way to say this, and the fact is you actually don't care if they're both above the x-axis, so that's why I drew G below here. So if we call this region R, the thing bounded on the left by A, on the right by B, above by F, and below by G, right? So I've just kind of shaded it in blue here. Then its area is always take the integral from your left bound to your right bound, and then the actual function you will take will be the top function minus your bottom function, okay? So let's go ahead and look at an actual example with real functions here, not just pictures. All right, so here are two actual functions. So we've got f of x is x squared minus 5x minus 7, some parabola, and g of x is x minus 12, which is a line, and we want to find the area between them from -2 to 5. So first of all, we have a graph, right? we're looking at -2 over here, and we have 5 somewhere over here. And so we need to figure out what is on top, right? And what is on bottom. So unless you already know exactly what they look like or have some graphing tool, the way you want to do this is look for where they intersect one another. So they're going to intersect when they're equal, right? They share a point. And so you're looking to solve for f of x equals g of x. So in this case, that means we write this, and then if you solve a few steps, you see that it solves out nicely. We get 2 roots, and so these guys are going to intersect at the right boundary here at x equals 5, and also somewhere in the middle at x equals 1. And so then we just need to get a few points here. So we know that the parabola goes through, its y-intercept is -7. The line intercepts at -12. And so let's just say I draw f in red and g in blue. Then the easier one to do is g, right? Because it is just a line, and it's going to look like this, right? It has slope 1, so by the time it hits 5, it's gone up to -7. And then it goes down over here at, this is -14. And then f, it's going to go through -7 here, and we know at 1, so at the y value -11, it's going to intersect the blue graph. And then we know it comes back up and it intersects again here. And so when we talk about the area between them, we need to see both of these regions. So first of all, let's see where this actually goes up. It's going to go up and hit at 7, right? Because we have 4 plus 10, 14 minus 7 is 7. And so we have 2 different regions that we're talking about here, right? We have this region over here between them where f is on top, and then in the yellow we have this region over here where g is on top. And so what do you think we do? Well, we're going to just split our integral right here at 1. So our area between them is going to go from -2 to the intersection point of f minus g plus the integral from 1 to 5 of g minus f, because here f is on top and here g is on top. And then these are both polynomials. It's pretty easy to compute these integrals. I mostly just wanted to show how to set this one up and not necessarily take the time to compute it. Okay, so on the first exercise, I want you to go ahead and find the area between these 2 parabolas on the interval from 1 to 3, which means you should be looking for where they intersect one another, and then in between these intersection points, which function is on top and which function is on bottom. All right, so let's do one more example and find the area of the region between x equals 9 minus y squared and x equals 5. So the first thing I want you to notice, right, is we've changed our independent variable and dependent variable, right? Now this is x as a function of y instead of y as a function of x. So you can view things in a couple ways here. So we know what these graphs look like, right? This is x starting at 9 down here, and then it's a downward facing parabola, except for it's not downward, it's leftward, because we have y instead of x, right? -x squared would face down, but this is moving horizontally, not vertically. And so we head back left. So this is 9 minus y squared. And then x equals 5 is just a vertical line, right? So we're talking about this region here. And so to find this area, you have a couple of options, and I want to talk about both of them. So you can just do top minus bottom as we did before, right? This is our top in red, and then our bottom here in green is this piece. So here we have to figure out, like, what are these functions, right? Because I was given a function in terms of y, not in terms of x. And so if I want to do like this integral from 5 to 9 of top minus bottom, I have to rewrite these. So this is really just the 2 pieces of x equals 9 minus y squared, right? You can solve for y as y squared is 9 minus x, and so y is plus or minus the square root of 9 minus x. And so the top is the positive square root, and the bottom is the negative square root. And so that's a little dx there. And so you would end up with the integral from 5 to 9 of 2 times the square root of 9 minus x dx. So this would work. Now it's going to require a little u sub there, and you have to deal with the square root, but it's not too bad, right? But you do have another option. So the other option is to change your perspective. So instead of always thinking of moving with regards to the variable x and then thinking top minus bottom, you can focus on the y-axis instead of the x-axis. And so here, your top, again in the red, would be looking from the perspective of the y-axis, so the top is like the furthest right, and then the left, or the furthest left thing, is going to be your bottom in this case. So if you want something with respect to y, right, you like do a dy, then instead of top minus bottom, it's going to be right minus left. Okay? And this can be useful sometimes, and we'll see why in this case. So you'll get a much easier integral that doesn't require like a u sub or have any square roots. The other issue is we need to find our bounds, right? So for x, we usually go from left to right. So for y, we should be going from bottom to top. So we need to find these intersection points, right? So what are those? Well, that's where 5 is equal to 9 minus y squared, or when y squared is 4. So these are plus or minus 2. So this is negative 2. This is 2. And so these are our bounds for our integral. And so when we actually input the functions here, we get 9 minus y squared minus 5. And this is actually just a really nice function, right? This is just a simple quadratic of 4 minus y squared. And so this is much easier to do the integration on. And notice, right, we didn't have to split into like two different functions here. It already was like nicely written as 9 minus y squared. So this is kind of an advantage you can have sometimes when you notice that maybe one axis is preferable to another. So I thought it was worth talking about doing things with the variable y, since we're always so used to doing everything with the x-axis as our main one. All right, so for your second exercise, I want you to use this new method. So I want you to use integration with respect to y to find the area bounded by these two functions. And you're going to have to find the intersection points to figure out what bounds you really need to use here. All right, thank you for watching.